So, greetings students, and in, today's class will be moving with your lecture side. Okay, so we've been dealing with your unit 4. So, in unit 4 deals with the measurement of your high voltage, okay, high voltage and high current. So, in this we have already covered the how to will be measuring your high voltage. Okay, so in the high voltage itself, there are 23 types, starting with your DC voltage, followed by your high AC voltage. After that, we have started with the high impulse voltage. Okay, so in this lecture 5, we will be moving to your current measurements. So, starting with, we'll be seeing your current measurements. So in this lecture, we'll be covering about the measuring techniques of the high current. So this includes the main four concepts or the methods, which are resistive shunts, Hall generator, magnetic links, and then your series resistance voltmeter. Okay, so we will be covering these four methods in this lecture. Okay, these four methods are very important for your current measurement. Okay, they might be separately asking each and everything as an 8-mark question. So high current measurement techniques, okay, similar to your high voltage measuring techniques, the high current measurement also can be classified into three types, starting with your DC currents, okay, so DC or direct currents. Then after that, we will be doing with your alternating currents. So in the alternating current, one is of your power frequency and another one will be of your impulse, okay, with a very high frequency. Okay, so for measuring your direct current, we will be making use of three methods, starting with the resistive shunts. Okay, this resistive shunts method is the common to all the three types. Okay, so resistive shunts can be used for both your direct current as well as your alternating current measurement. After that, we will be making use of Hall effect generators. So we'll be seeing your Hall effect generators. We'll be seeing your Hall effect generators, and after it, that will be going with your magnetic links. So in this, the most important point is your Hall effect generator. Okay. So this Hall effect generators also you might have studied at your school level, as well as in the primary physics also you might have studied. So based upon the Hall effect, how we will be measuring it, we can see in this lecture. So after that, for your AC current, we will be making use of the restrictions again. Afterwards, we'll be making use of electromagnetic current transformers. So this current transformer uh, measurement is similar to your CT. How you'll be measuring is your CT and PTs. The same principle will be using in your electromagnetic current transformers. So this CTPT measurements you might have learned your measurements and sensors and measurements subject. And after that, for measuring your high AC impulse current, you will be making use of resistance again. Again, you'll be making use of a Hall effect generators. Then we'll be making use of a point called Rogowski coil. Okay, this Rogowski coil also will be making use. Okay, so in these things, the most common part is here these four methods. Okay, we'll be seeing in this lecture. So starting with resistive shunts. Okay, so what this resistive shunts will be doing? So our ultimate aim is to measure a very high current. Okay, we have to measure a very high current. So this resistance can able to measure both DC as well as AC. I have already said. So then it doesn't depends upon the nature of the current. So in general, what happens is that a high magnitude DC current Okay, so here we are taking the DC current or measured using a resistive shunt, okay, of a low ohmic value. So here in general we'll be making use of a very less resistor value, okay, because the resistor is a component which limits your flow of the current. So if the resistance value is minimum in the circuit, the power flow or the current flow will not be affected. So for that instance, we will be taking the resistance value to be a minimum. Okay, for that purpose only, we will be taking the resistance value to be as a minimum concept. So based upon this, usually the resistance will be chosen between 10 micro ohm to 13 milli ohm. Okay, so this is the range in which the resistance will be chosen. And the principle behind this restitution is that depending upon the heating effect, okay, as the current flow is very high, there will be the less amount of resistance to the flow of current. So due to the high flow of current, there might be some heat dissipation in the resistance. Okay. So here what happens, the high current resistors are usually immersed in the oil. Okay. So they'll be immersed in the oil and are made as a 3 or 4 terminal resistance. So in order to safeguard the resistance from a very high current, generally what they'll be doing is they will be shielding it by immersing the resistance in an oil. Okay, and then they'll be make it as a 3 or 4 terminal resistance. Okay, in this as shown in the second diagram. Okay, so in this there will be CC. So here this is a 4 terminal resistance. So the CC corresponds to your current terminals and PP corresponds to your potential terminals. Okay. So the voltage drop across the shunt is limited to the few millivolts. So here, what they'll be doing is they'll be allowing a very high current to flow through it. Okay. Based upon the current flow, the voltage drop will be minimum as the resistance value is minimum. So as per the basic Ohm's law, so for the linear circuits, your voltage measurement V is directly proportional to I at constant temperature. Okay. So for that we will be introducing a constant which is nothing but a resistance. That's what your Ohm's law implies. So here what we'll be doing is we'll be passing a very high current and based upon the heat dissipation, the current value will be we can able to measure. So that's what we are doing. So second one is here, very important one, Hall generator. Okay. So about this Hall generator, you already studied. Okay. So I don't need to explain so much elaborately. So generally, what happens? There will be an element. Okay. Will be passing an electric current through the metal plate. So here, this will be the metal plate, and will be passing through the current through this metal plate, and this metal plate will also be subjected to a magnetic field. And how this metal plate will be subjected to magnetic field means it will be in a perpendicular direction to that of the flow of current. Okay, so the flow of current and the magnetic field D will be 90-degree apart from each other. Okay, so based upon this, what happens? Lorentz force will deflect. The force will be generated, so that force is nothing but called Lorentz force. So according to this, we have already studied this in your physics. So based upon this Hall generator, the equation what we have learned was F equal to BIL sin theta, right? So in that sin theta, you will be putting 90 degrees. So sin theta will become 1. Okay, theta will be putting 90 degrees, sin theta will become 1. So F equal to BIL will be coming. So that F is nothing but your Lorentz force. So what this Lorentz force does, it will deflect the electrons in the metal structure. in a direction normal to the direction of both current and the magnetic field. So what they're saying is that this Lorentz force, what I have said was a force which is perpendicular to both your current and your uh, magnetic field will deflect the electrons in the metal structure. Okay, they deflect the, already current is nothing but the flow of electrons. So these electrons will be deflected. So how it will be deflected? It will be deflected in the direction perpendicular to the direction of both magnetic field and current. Okay, so this is the basic principle of your Hall's generator. So based upon this, the charge displacement, okay, the charge displacement, uh, due to the Lorentz force, there will be the charge displacement occurs. Okay, the electrons will be deflected perpendicular to both your current electric field as well as your magnetic field. So based upon this, there will be a charge displacement. This charge displacement will be responsible for generation of an EMF. So this EMF is called as Hall voltage. Okay, Hall voltage. So this Hall voltage is represented by VH. Is represented by VH. So this VH will be equal to R BI by D. So this R is very small in case of a metals. So R is nothing but the resistive material. Okay, you already know metals will be conducting for a very will be having very good conductivity. So the resistivity will be very minimum. So that's what they are saying over here. And for the semiconductor, this will be high. So this is the basic principle for the Hall generator. Now our approach is based towards your current measurement. So in case of a large current measurements, the current carrying current conductor. Okay, so the current carrying conductor is shown over here. The current ID is flowing through this current carrying conductor. Is surrounded by an iron core magnetic circuit. So this iron core magnetic circuit is what gives out your magnetic field. Okay, and at the same time, this iron core will be subjected to the electric field also. Okay, the current will be flowing through the magnetic core also. So the magnetic field density H is equal to I by L. Okay, so this magnetic field is produced in a small air gap in the core. Okay, so this is your metal plate which is kept between this magnetic core. Okay, so based upon this current flow, this Hall voltage will be varying. Okay, if you are measuring with respect to this Hall voltage, the value means you can get the value of the current flowing in this current carrying conductor. Okay, so this is the principle behind your Hall generator and measurement of the large current with your Hall generator. So next one is your magnetic links. So what are these magnetic links means? So these magnetic links are nothing but short retentive steel strips. So we have already seen with respect to your series resistance concept in your high DC voltage measurement. Similar to that, here also will be making use of such kind of arrangement. So magnetic links over here are short, high retentive steel strips. Okay, how they will be arranging? They will be arranging a circular fashion. Okay, so these strips have the property that the remnant magnetism. So remnant magnetism is nothing but the residual magnetism for a current pulse of 0.5 bar 5 microsecond, the same as that of a caused by a DC current. Okay. So here what they are saying is they are equating your magnetic field, okay, with your DC current. Okay. So they are giving an analogy with respect to the electric field as well as your magnetic field. Hence, these can be used for the measurement of peak value of impulse current. So how these strips will be kept means these strips will be kept at a known distance. Okay, will be kept at a known distance, and these are useful for field measurement, maintaining for estimating the lighting currents. Okay. So mainly they'll be used in the transmission lines for the measuring of your lightning currents. Next is your series resistance voltmeter. So this is a very simple concept. This is also based upon your Ohm's law. This is also similar to the same thing what you have seen in the measurement of your high DC voltage. Okay, what they'll be doing is they'll be applying your high voltage and they'll be using a very high resistance. Okay? And this resistance will be connected to a microammeter. And based upon this microammeter, you can see the measured area of current. Okay? So this is complete today's lecture. And in this, the main thing what you can expect is you can expect your Hall generators and your restrictions. And another one question is that Rogowski coil is there. It is also an important question. Okay. And I'll be showing a video regarding your Hall effect. I'll be showing a video.
Hello, Daniel here from howtomechatronics.com. In this video, we will learn what is Hall effect and how Hall effect sensors work. The Hall effect is the most common method of measuring magnetic field, and Hall effect sensors are very popular and have many contemporary applications. For example, they can be found in vehicles as wheel speed sensors, as well as crankshaft or camshaft position sensors. Also, they are often used as switches, MEMS compasses, proximity sensors, and so on. Now, we will go through some of these sensors and see how they work, but first let's explain what is the Hall effect. Here's the experiment that explains the Hall effect. If we have a thin conductive plate as illustrated and we set current to flow through it, the charge carriers would flow in a straight line from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow of the charge carriers due to a force called Lorentz force. In such a case, the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means if we put a meter now between these two sides, we will get some voltage which can be measured. So, the effect of getting a measurable voltage, as we explained above, is called the Hall effect, after Edwin Hall, who discovered it in 1879. The basic Hall element of the Hall effect magnetic sensors mostly provides very small voltage of only few microvolts per Gauss, so therefore these devices are usually manufactured with built-in high-gain amplifiers. There are two types of Hall effect sensors, one providing analog and the other digital output. The analog sensor is composed of a voltage regulator, a Hall element, and an amplifier. From the circuit schematic, we can see that the output of the sensor is analog and proportional to the Hall element output or the magnetic field strength. These type of sensors are suitable and used for measuring proximity because of their continuous linear output. On the other hand, the digital output sensor provides just two output states, either on or off. These type of sensors have an additional element, as illustrated in the circuit schematic. That's the Schmidt trigger, which provides hysteresis or two different threshold levels, so the output is either high or low. For more details how the Schmidt trigger works, you can check my particular tutorial for that. An example of this type of sensor is the Hall effect switch. They are often used as limit switches, for example, in 3D printers and CNC machines, as well as for detection and positioning in industrial automation systems. Another contemporary applications of the Hall effect sensors are measuring wheel speed or RPM, as well as determining position.
So this is how your speedometer works. Generally, the speedometer will be based upon the Hall effect sensor, and here they will be saying how it works. The
Of
speed ruler.
crankshaft or camshaft in engine systems. These sensors are composed of a Hall element and a permanent magnet, which are placed near a tooth disc attached on the rotating shaft. The gap between the sensor and the teeth of the disc is very small, so each time a tooth passes near the sensor, it changes the surrounding magnetic field, which will cause the output of the sensor to go either high or low. So, the output of the sensor is a square wave signal, which can be easily used for calculating the RPM of the rotating shaft. Thanks for watching, and for more tutorials, visit my official
And next video will be based upon the restrictions. Okay, consider restrictions. How you see the restrictions in the measuring?
So what exactly is a shunt? Well, a shunt is used to measure current. For example, the amp meter on the front of my power supply uses a shunt to measure the output current from the power supply. So in a nutshell, a shunt is just used for measuring current. But what does a shunt look like exactly? Well, for example, this is an axial style shunt, and this is a high current shunt rated to handle up to 50 amps. In this rather
So here
ordinary
you can
looking
see
wire jumper
the
on the
structure
circuit
he
current.
showed.
For example, the amp meter on the front of my power supply uses a shunt to measure the output current from the power supply. So in a nutshell, a shunt is just used for measuring current. But what does a shunt look like exactly? Well, for example, this is an axial style shunt, and this is a high current shunt rated to handle up to 50 amps. And this rather ordinary looking wire jumper on the circuit board is also a shunt. So shunts come in a wide range of varieties. So what exactly defines as a shunt then? Well, in a nutshell, a shunt is nothing more than a conductor which has some value of resistance, typically in the milliohm range. Basically any conductor such as an ordinary resistor, this wire rod, or a length of copper wire could be made into an improvised shunt provided it has some resistance and we know the value of said resistance. A typical multimeter is useful for measuring the resistance of components down to say 1 ohm. However, they are unsuitable for measuring the incredibly low resistance of the shunt, for example. You can see my meter reads all zeros while measuring the resistance of both shunts. Now, although the resistance is incredibly low, it is there, and that's what makes a shunt useful. So basically a shunt is a low value resistor. Okay, great, but how does a shunt help us measure current? Well, that's a great question, and weirdly, to measure current with a shunt, we actually measure voltage. Let me explain. Have you ever found yourself situated in a paddock full of cows and need to order circuit boards? Yeah, me neither. But if I did, I would use this video's sponsor, JLC PCB. 5 circuit boards cost as little as $2. They offer fast production time and with a multitude. Next I'll add a 1 amp load over here. And lastly we have a power supply. The power supply voltage is irrelevant for the purposes of calculating current. 1 ohm shunt. Maybe
So
I'll
let's
shunt
go
how
through this
much current.
video to get a clear idea about the shunt also. Okay, I'll be closing the lecture with this and uh, I'll be closing the lecture with this and